Swayam Prabha. Digital India. Educated India.
Let's look at some more examples. Look at the row vectors with complex entries, and that becomes a complex vector space with respect to addition of row vectors. Yeah, and then we can similarly define complex vector space of complex vectors with n complex components. And depending on the context, Cn will again refer to either the row vectors or column vectors with n components. Now look at this. This is a very different example than the usual vectors. Yeah. So look at all functions from this closed bounded interval, real valued functions. Okay? These are real valued functions. And take a set of all possible real valued functions. This is a huge set. Okay, all functions that you encounter, yeah, in one variable calculus, they are in this set. It's a huge set. And take this field of scalars to be real numbers. I want to convert the set of all functions into a real vector space, real valued functions on closed bounded interval into a real vector space. In order to convert this into a real vector space, I must define addition of functions. I must define scalar multiple of a given function. So this is how we do. So take two functions from V, and then there is sum. Their sum is again a function from AB to R, and we define this f plus g operating on x is simply fx plus gx. Okay. This is how we added functions in calculus, and this is the addition of functions we are taking to convert V into a vector space. How do we do scalar multiplication? Well, take a scalar and take a function, then a times f is another function, but a times f operating on a real number x from this closed bounded interval is equal to a times fx. This is again a function. This is the scalar multiple of f. So we have defined addition of functions. We have defined scalar multiple of a function. And the field of scalars is real. So this is, you can check that the 8 axioms for addition and scalar multiplication, they are satisfied. Okay, they are satisfied. So this becomes a real vector space. And this is denoted by RAB. Right? This is denoted by RAB. In some sense, this is an analog of Rn. Okay. Rn, we have vectors with n components. Okay, they are vectors with n components, and RAB denotes functions from AB to R. Okay, and this is a vector space with respect to the addition. Now let's look at a subset of V. Okay, let's look at subset of V. So polynomials also give rise to real valued functions on the entire real line. Okay, entire real line. So look at polynomials of degree at most n and with real coefficients. This is a polynomial degree at most n with real coefficients. Okay, P and R. And you know how to add polynomials, how to multiply a polynomial by the real number, and these two operations will again convert P and R into a vector space. This is a vector space under usual addition of polynomials and multiplication of real numbers. So polynomials of degree at most n, they form a vector space. I can look at polynomials of any degree also. That's also a vector space. Okay. This is considering all functions, real valued functions defined on any closed bounded interval. I can also look at functions defined on the entire real line, functions from R to R, okay, or functions from Rn to R, okay, or functions from Rn to Rm. They all form vector spaces. So it's a very general notion. You have seen many vector spaces without knowing them. Yeah. Now look at this restriction. Instead of looking at arbitrary functions, I will look at only the continuous functions. Okay. So continuous functions, you know this notation from calculus. This is denoted by CAB. So real valued continuous functions on closed bounded interval. That is a real vector space under addition and scalar multiplication of functions, which I defined earlier. So CAB is really a subset of RAB. RAB was consisting of all functions from AB to R, real valued functions defined on the closed bound interval. But CAB is only taking the continuous functions defined on closed bound interval, real valued functions. This is a vector space, very important vector space in applications. One can restrict further and look at those functions which are differentiable at a point. fix a point in the closed bounded interval. Yeah, fix a point on the closed bounded interval, and the take functions which are differentiable at that point. Okay, then under addition and scalar multiplication, it is a vector space. You know that sum of two functions which are differentiable at a point is again differentiable at that point. Or if you multiply a function by a scalar, and then again it is differentiable at x. Okay, so differentiable function at a single point in a closed bounded interval, they form a vector space. I can look at differentiable functions which are differentiable at every point on the closed bounded interval. They will also form a vector space that will be contained in this. Okay, yeah. Now a slightly different example. Look at this second order differential equation. Y double prime plus ay prime plus by. Yeah, y is an unknown function. Y double prime plus ay prime plus by. A and b are real numbers. Look at, and this is a homogeneous differential equation, ordinary differential equation with constant coefficients. And this homogeneous equation has the property that if I take two solutions and add them, again I get a solution. Okay, so this is like the homogeneous system of linear equations. I have certain number of solutions of a system of homogeneous equations. I can add them. I can take any scalar. I can take any linear combination of solutions of ax equal to 0. Again, I get a solution. Same thing happens for this homogeneous differential equation y double prime plus ay prime plus by equal to 0. And if a and b are real numbers, then the set of all functions, all the functions, they have to be twice differentiable, right? They have to be twice differentiable. They form a real vector space. Okay, so solutions of homogeneous differential equation, then differentiable functions, continuous functions, all functions or vectors. So such variety of objects are forming vector spaces. Look at another variety of vector space. Take m by n matrices with real entries. So I fix m by m and n, and look at the set of all the matrices of fixed size m by n. Okay, we know how to add matrices of same size, and we know how to take scalar multiple of a matrix, m by n matrix. Again, it is an m by n matrix. Yeah, and these two operations, addition of two matrices and scalar multiple of a matrix, they satisfy those 8 axioms of a vector space. You can check. So this is the space of m by n matrices. This is again a vector space. So these examples indicate that the notion of vector space is very general. Okay, many kinds of mathematical objects that you have come across since your school days, numbers which are of real numbers or complex numbers, matrices, functions, differentiable functions, okay, all of them are they form vector spaces. So the notion of vector space is very, very general, but it is defined in axiomatic fashion. When we write definition of vector space, we are not telling what is the operation. Yeah, how to add vectors or how to multiply a vector by scalar, we are not specifying that. Instead, we are specifying the properties that these two operations follow. Because when you do computation, you are actually using the properties of these two operations, okay, in a given context. So it is those 8 fundamental properties mathematicians extracted, that in large number of computations we are using these 8 properties. So they made a axiomatic system, and that is called vector space. And then vector spaces are studied abstractly. And then if you prove a theorem about vector spaces, it is simultaneously applicable on the set of matrices, on solutions of differential equations, or solutions of homogeneous linear equations, or the vector space of functions, or vector space of differential functions. Such wide variety of applications it will have. So by abstracting all these objects into the concept of a vector space, we are actually achieving an efficiency. So a result proved about abstract vector space is simultaneously applicable in all these examples. So this is a level of abstraction, and you have to get used to this. Okay. Yeah. Let us look at the concept of subspace of a vector space. So let V be a vector space over a field of scalars. Yeah. A non-empty subset W of V is called a subspace. if the following properties hold, the zero vector belongs to W, and if U and V are in W, their sum is in W, and W is closed with respect to scalar multiplication. Yeah? So W is closed with respect to addition and scalar multiplication. The zero vector of V belongs to W. W is a subset of V. Then W is called a subspace. Okay. Now we have come across many subspaces already in the list of examples that I gave you. So take a vector space and suppose x1 up to xn are vectors in V and ci's are scalars. Yeah. Then I look at the cixi, that is a scalar multiple of xi, and add these vectors. Yeah. This is called a linear combination of xi's, and ci's are called the coefficients of xi in this linear combination. So imagine an abstract vector space. I take finitely many elements, which we call as vectors, and we can form a linear combination. The coefficients are scalars. Okay, so this is called a linear combination. Then a subset S of a vector space over F, then the linear span of S is the subset of all vectors which are expressible as linear combination of finite subsets of S. So I have an arbitrary subset of a given vector space. Okay, then I take all possible finite linear combinations where the vectors are drawn from this subset. Okay, so fix a subset of V and then take all linear combinations of vectors of S, and this is called the linear span. So I get other vectors in the vector space. It may, the given linear combination may not be in the set S, right? So then the all possible linear combinations of finitely many elements of S, this is called the linear span. Okay, this is called linear span. So linear span of S is simply sum of cixi, where n is a finite number, xi's are elements of S, ci's are scalars. We say that Ls is spanned by S, or Ls is the linear span of S. Okay. So simple example, R2 is linear span of E1, E2. Right? In the Cartesian plane, I have the unit vector I and unit vector j, and I take all possible linear combinations of I and j, I get all vectors in the plane. Or take the three-dimensional space R3. I have three unit vectors I, j, k. Okay, and these three unit vectors along the x-axis, y-axis, z-axis. If I take all possible linear combination of these three unit vectors, I get the entire space. So entire space has infinitely many vectors, but we are writing the infinite space as in terms of a finite set. Okay, in terms of finite set that identify a subset of the vector space, so that all vectors are actually in the linear span of this finite set. Many times we can do it, many times we cannot do it. Yeah. So we may not be able to find a finite subset of vector space so that all vectors in the given vector space are in the linear span of a finite set. Okay, we'll come back to that. Okay, so let us see that Ls is the smallest subspace of V containing S. Okay, so inside V, so V is a big space. Okay, V is a big space. It can be Rn or space of functions. Inside V, I take a finite set or some subset, and I generate all possible linear combinations. Okay, then I get the linear span. Let us show that among all these subspaces of Rn, the smallest subspace which contains S is exactly the linear span. Okay, Ls is the smallest subspace of V containing S. So first of all, we need to see that Ls is a subspace. Yeah, Ls is a subspace. So Ls consists of linear combination summation xi, xi, ci, xi, where xi's are vectors and ci's are scalars. So I take two such linear combinations, di, xi. Then I can add them, and I get another linear combination, ci plus di times xi. By properties of addition and scalar multiplication, it is clear that sum of these two linear combinations is again a linear combination. Okay, that is in Ls. And if I take a linear combination and multiply by a scalar that is equal to sum of alpha ci xi. That is again a linear combination. Okay. So to show that LS is subspace, I have to show those properties that it is closed with respect to addition, scalar multiplication, and the zero vector lies in this. But zero vector is simply I take Ci is equal to 0. Yeah. So LS is subspace, and if W is a subspace of V which contains LS, then W is closed with respect to taking linear combinations because W is a subspace. So W is going to contain LS. Yeah? The linear span of S is contained in W. W is a subspace which contains S because W is closed with respect to addition and scalar multiplication. Okay. Yeah. So this is the every subspace of V contains LS. LS is itself a subspace, and therefore LS is the smallest subspace of V containing S. Yeah. So many times in a given vector space, I want to study some finitely many objects. Okay, the properties of these finitely many objects. But I'm not able to apply the theory of vector spaces. So I then enlarge this finite set of objects. I take all linear combinations of these objects in a given vector space. Then I arrive at the smallest subspace which contains these elements. And that is the linear span. Okay, right? So this leads to the notion of 4 fundamental subspaces associated with to a matrix. This is very important concept in linear algebra. Later on, I will prove a theorem called the fundamental theorem of linear algebra, which is about these 4 subspaces. Yeah? These 4 subspaces are arising out of a given matrix. Okay. Our real purpose is to understand matrices, and understanding of matrices makes it the solving system of linear equations more efficient. And the matrices which arise in various operations in linear algebra, they are associated to these, they give rise to these 4 fundamental subspaces. Let's see what these are. Okay. So I fix a matrix. It is a rectangular matrix, M by N, M rows and N columns. I look at the row space. Okay. So the rows, there are M row vectors. The M row vectors, the row vectors lie inside Rm. Yeah, they lie inside Rn. The row vectors have it's an M by N matrix. So each row vector has N components. There are M rows. So the row vectors are lying inside Rn. And the column vectors, take the column vectors of the given matrix, they live inside Rm. So if I have this M by N matrix, the row vectors live inside Rn, the column vectors live inside Rm. Okay. So take the row vectors. There are M row vectors living inside Rn, and I can take their linear, that is called the row space. Okay. The M row vectors in a M by N matrix, they are all living inside the big space Rn. I take its linear span, that is called the row space. Null space is defined to be set of all vectors in Fn so that Ax is 0. So these are solutions of homogeneous system of linear equations. Okay. Ax equal to 0, and it is clear that this is a subspace because if I add 2 solutions of Ax equal to 0, I get another solution. I multiply a solution by a scalar, I get another solution, and 0 is a scalar. So this is a subspace. Na is a subspace, and this is again a subspace of Fn. F is my field of scalars. I should be careful. This is Fn. So null space is contained in Fn, and the row space is also contained in Fn. There are 2 counterparts of these subspaces. Yeah, the null space of A is the set of solutions of homogeneous linear equations. So Na is a subspace of Fn. The column space of A. Yeah, I look at the column vectors. The column vectors are living inside Fm, and take the linear combination of all column vectors of the given matrix, and this set is called the column space. Okay. Yeah. So the column space, columns of a matrix are the row vectors of transpose. So column space of A is really the row space of A transpose. So in this sense, this space is the counterpart of row space. So we have a counterpart of null space also. We have counterpart of null space also. So to understand that, suppose AX is 0. I take transpose. Then X transpose, A transpose is 0. So these are solutions when we multiply A on the right by X. But here this X transpose is a column vector, is a row vector. This X is a column vector. X transpose is a row vector, and it transposes n by n matrix. Okay. Yeah. So this gives rise to the fourth space. This is called the left null space. All vectors in Fm so that Xa is 0. Yeah. A is m by n. So I can multiply this by a row vector which has m components. Okay. So X is in Fm so that Xa is equal to 0. Right? This is also a system of linear equations, homogeneous linear equations. But now we have how many equations are there? As many as number of column vectors, and there are as many indeterminates as the components of this row vector. So this is in a sense, this is the counterpart of Ax equal to 0. This is the null space of A, and this is the null space of A transpose. Okay. This is the null space of A transpose. Because if Xa is equal to 0, this implies A transpose, yeah, X transpose equal to 0. So X transpose will be in the null space of A transpose. So think of X transpose as a column vector with m components. So this is called the left null space. So we have row space of A, we have null space of A, we have column space of A, and left null space of A. So these are the four subspaces which are derived from the given matrix. So our system of linear equations give rise to a matrix, m by n matrix, and this m by n matrix give rise to four fundamental subspaces associated with the matrix: the row space, the null space, the column space, and left null space of A. These four spaces are intimately connected. Okay. We'll continue to return to this, and later on I will draw a diagram which connects the four subspaces. Okay. I think our time is finished, so I will stop here.